So, I recently got my hands on the new 14 and 16-inch M1 MacBook Pros with the M1 Pro and M1 Max chips in them. And one of them is for my girlfriend, who is currently doing her graduate studies, and another one was for me, both for work and school and research. So, here's a 14-inch, 16 inches on the desk behind me. And I wanted to see how these chips performed in scientific workloads. There's plenty of benchmarks online showing how they perform in things like Cinebench, in games, in generic things like Geekbench, but not that much covering how they fare in scientific workloads, which is something that is particularly interesting to me since it's what I do all the time. So the main reason we bought these machines was to replace our old ones. My girlfriend used to run a 2014 MacBook Pro 13, which at this point is pretty old. It was chugging along. And then I was looking to replace the work machine that I had, which was a 2017 MacBook Pro 15. Both of these machines were getting pushed beyond what they could reasonably handle with our workloads. And based on the reviews that came out, it looked like the new generation was a pretty significant leap, and it was probably a good time to upgrade. If you like scientific computing and are interested in programming, please like and subscribe. I'm going to be putting out more videos, starting with a series on introductory Python for scientific computing, and we'll work our way up to more intermediate and advanced topics, both in general software engineering and specifically also scientific computing. Oftentimes when I'm talking with people about heavy computational workloads in scientific and engineering contexts, the question comes up, why not just use cloud infrastructure? It's scalable and you can pretty much get a limitless supply of it. Or why not offload your work to a compute cluster? And these are both very valid points. Typically for production workloads, you do exactly that. You put it on some really beefy auto-scaling cloud infrastructure and you don't worry about it. It always has extra headroom. Same with research tasks. There are university and Canada-wide research compute clusters that we use, and those can give you a lot of horsepower, and for researchers at least, they're typically free. You just need a book time. So why would anyone get a really powerful laptop in that case? What's the point of it? Well, not all of the work that you're doing ends up being something you're deploying to production or something that you can request compute resources for, like in a cluster. A lot of the time, in fact, definitely a majority of the time, you're doing some form of rapid prototyping, trying to get your proof of concept off the ground, be it in a software engineering or a research capacity. And in those cases, it makes a lot of sense to have a strong local machine because you're typically going to be doing that prototyping on a local machine. You don't want to have to deal with the overhead of managing cloud resources or booking time on a compute cluster just to try out something that may only take 5 minutes or 10 minutes. So for these benchmarks, I chose two projects that I'm actively working on right now. One of them is an epidemiological simulation framework, and the other is a deep learning problem. Each of these is relatively heavy in terms of their resource usage, and each of them requires a lot of active prototyping. So there's no opportunity to simply offload it to the cloud or to a compute cluster and let it run that way. I will be testing multiple tasks under each of these projects on all four of the machines, the new MacBook Pro 16 and 14, as well as my old work machine and my desktop. Each benchmark will be run 5 times on each machine in order to get a statistically meaningful result, and these results will be compared. Alright, I'll put the specifications of all the machines up on screen right now. You can pause the video if you want to look through it, and let's get right into the results. Starting with the single core simulation result, we can see that the M1 Max and M1 Pro are pretty much tied up at around 13 minutes, 30 seconds. This is quite a bit faster than the Ryzen 5, which clocks in at 18.5 minutes, and it's way faster, almost twice as fast as the Core i7 and the MacBook Pro 15, which takes a whopping 26 minutes. If we move on to multi-core, we can see that the trend of M1 Max and M1 Pro being the same sticks, because these are both CPU tests and they effectively have the same CPU. The Max just has a better thermal solution. Now we can see a much larger gap growing between the M1 processors and the competition. This really shows how effective those efficiency cores are along with the performance cores, despite having a lower thread count than the Ryzen 5 3600. Going back to a single core benchmark, we then have the simulation animation. This is sort of like a rendering test, but it's not GPU accelerator or anything. And again, the M1 Max and M1 Pro are head-to-head, with the Ryzen 5 falling behind and the Core i7 just absolutely left in the dust. Moving on to the deep learning benchmark, we can see that the M1 Max and M1 Pro are no longer providing the same performance. This is due to the deep learning test leveraging the GPU of the M1 Max, which has 32 cores as opposed to the M1 Pro's 14 cores. This is a bit of an unfair test for the Ryzen 5 since it doesn't have an integrated GPU to leverage. That machine does have an RTX 2060 Super, but I feel that a dedicated GPU is a bit more unfair than just comparing it against the CPU. Lastly, let's look at Geekbench. Geekbench isn't a particularly useful benchmark, but it's general and it offers an avenue for comparison for any other hardware out there. For the single core scores, we can see that the M1 Max and M1 Pro are again smashing the other two. If we then move to the multi-core score, we can see that the Max and Pro are absolutely crushing it with over 12,000 points compared to 7,000 for the Ryzen 5 and barely over 3,000 for the Core i7. This makes the new M1 MacBooks about 4 times faster in heavily multi-threaded workloads as compared to the old 2017 MacBook Pro, which is pretty crazy considering there's only 4 years between them. The reason that I parameterized all of the benchmarks that I ran personally in terms of time is because that's one of the most meaningful ways to contextualize these results. You can look at a score and you can say, oh, it's 5 times better score, but what does that really mean? But when you look at time taken to complete some sort of task, you can then translate that into more tangible concepts such as billable hours or research throughput. If you treat your computer as a tool, it makes sense to get something that's faster when you're using it for professional applications because at the end of the day, time is money. So even if something is marginally faster but costs a lot more, as long as you can recoup that investment, it's probably worth it. That's why you see workstations that cost tens of thousands or hundreds of thousands of dollars for things like data center applications or film production, whatever requires a lot of compute power, because financially, these big investments end up making sense. And while I am far from something like that, it still makes sense for me to have a powerful machine so that I can focus on the science and focus on the engineering instead of just sitting there waiting for my results to compute. Thank you all for watching. If you guys enjoyed this video, please like and subscribe and stay tuned for more videos.